Q calculations, you'll actually be given mixed examples. So we won't just be using one formula at a time. You'll actually have to assess a problem and determine which formula you're going to use. So here's some keywords up here, and I want you to think about which formula would go with which. So take a minute, pause the video, and write the formula that would go with each of these keywords next to them in your notes. So the equation that we would use if we're melting is our heat of fusion equation. If we're changing a sample from a liquid to a gas, we would use our heat of vaporization. A temperature change, Q equals mc delta T. If we are vaporizing something, Q equals mHV. Freezing, the opposite of fusion. If we're doing something to a sample at its boiling point, that's vaporizing. A change in temperature tells us delta T equation, and condensation is that same kind of phase change as vaporization. Vaporization and fusion are the two easiest to confuse. That's why they're very commonly put on part 2 of the Regents, because you're very likely to reverse which one is which. So now we're going to take a moment and we're going to walk through some of these, and we're going to look very carefully at what equation we would need. How much heat is needed to melt a 340-gram sample of ice? So my big key word here is going to be melt. Melt tells me that I'm going to be using Q equals mHF. What I know from this equation is my mass is 340 grams. I know my heat of fusion, and again, I'm talking about ice, so that's a version of water, so I can use my constant from table B. I am going to talk about an example where that's not actually the case. My heat of fusion is 334 joules per gram. So the amount of heat will be 340 grams times 334 joules per gram, which should give you approximately 113,560. If we wanted to round this to proper sig figs, that would be 114,000 joules. If we wanted to vaporize, that tells me I'm using Q equals mHV. So in this case, I know my mass is 560 grams. I'm talking about a sample of water, which means I'm using my constants from table B. Heat of vaporization, 2,260 joules per gram. Q equals 560 grams times 2,260 joules per gram. So you're simply multiplying these. Again, you're going to get a big number for this. The heat of vaporization is big, so that makes sense. And if we needed to show this with proper significant figures, we're able to have 3. So 127,000 joules with proper sig figs. How much heat does a 600-gram sample of water vapor, water is important, lose as it's converted to liquid water? So we're taking vapor, which is a gas, and turning it into a liquid. So this is another Q equals mHV. We have a mass of 600 grams. We have a heat of vaporization of 2260 joules per gram. So we're going to plug in 600 grams times 2,260 joules per gram. We're multiplying this. Again, if we have to adjust this for significant figures, the 3 sig figs in our answer. How much heat is needed to raise the temperature of 300 grams of water, 45 degrees or 45 Kelvin? So we're raising the temperature. We're using Q equals mc delta T. Our mass is 300 grams. Now, there is only one temperature given, but that actually is the change in temperature that we want. So our delta T, the amount we want to change the temperature by, is 45 Kelvin. So we'll plug in our mass of 300 grams our specific heat capacity of 4.18, and our change in temperature of 45 Kelvin. Simply multiplying through, you get 56,430. We're actually limited to only 2 sig figs here, so this would actually round to 56,000 joules. If 234,000 joules of heat energy is needed to heat a sample of water, so that's important. We have a temperature change, 307 to 312. That tells us that we're going to be using Q equals mc delta T again. Sorry, mass is what we're actually solving for this time. In this problem, they're giving us our heat. Our change in temperature is 312 minus 307, or 5 Kelvin. So we're going to plug into our Q equals mc delta T equation. Actually, sorry, I don't really need to rewrite that. Our M is what we are, oops, sorry, having a moment. All right, here we go. 234,000 joules. Our M is what we're solving for, 4.18 joules per gram Kelvin, and our change in temperature is 5 Kelvin. Because we really do have 3 sig figs here, we are going to be able to actually keep 3 sig figs in this answer if we want. That kind of is allowed here. I know it looks like there's only one because of that 5. So you're going to do 234,000 divided by your 4.18 times 5. Should give you 11,200 with 3 sig figs. Now, number 6 is a little bit more challenging, so there's a lot going on here. The temperature of 50 grams of water is raised to 323, so we have temperature being raised, Kelvin, by the addition of 1 kilojoule of heat. What is the initial temperature of the water? So we know we have a change in temperature occurring. So our givens that we have our mass of 50 grams. We know we have C, 4.18 joules per gram Kelvin. We have a T, but we don't actually have a delta T. We want to get to the temperature of 323 K. That's not a delta T, that's just a final temperature. And we have Q, which is given in kilojoules. I'm going to go ahead and convert this to 1,000 joules. So when I plug into my equation, my 1,000 joules need to go on the left side. My 50 grams of water is going to go here. My 4.18 joules per gram Kelvin is going to go here. A lot of people are tempted to plug that temperature in, but that's not our change in temperature. We're actually solving for change in temperature. So what you're actually going to do first is go ahead and solve for that change in temperature. And the change in temperature that you should get from this is 4.78 Kelvin. Through this problem, my sig figs are right here. I've got 2 sig figs. So I can also call this 4.8 Kelvin. But you don't need to round till the end. So they told me that I am adding heat and raising the temperature to 323. So if I'm adding heat and ending up at that temperature, that means I used to be at a lower temperature. So my final temperature is 323. What I want to know is my initial temperature. So I am now at 323, and I made the temperature go up 4.8 degrees. So 323 minus 4.8 is going to give me my final answer. I guess I haven't quite rounded in that one, of 318.22 degrees Celsius. This is a little tricky with sig figs. We would actually have to go down to 2 sig figs, which would make this 320K if we went to our proper number of significant figures. Next problem I wanted to show you is an old regions problem where they had you do a Q calculation with a substance other than water. So the specific heat of water, that 4.18, and notice these are in degrees Celsius. The older regions used to use that. It means the same thing. I could replace that with K. Totally allowed, doesn't make any difference. So they actually had an old problem about this, so I figured it was an important thing to address. If we applied heat energy, the same amount to each sample given here, so 5 grams of water and 5 grams of aluminum, what would the final temperature of each block be? So go ahead and pause the video and solve for each one. So for my water, and again, I'm using Q equals MC delta T for both of these. The amount of energy for each of these is 836 joules. Mass for each of these is going to be 5 grams. For water, I'm still using that 4.18. And then I want to know what my delta T is. My setup for my aluminum block over here, same formula, same amount of energy that I'm putting into each of these, same mass. However, this time my specific heat is a little bit different. My specific heat for aluminum is 0.987 joules per gram Kelvin, and I'm still solving for delta T. So in solving for delta T for each of these, I'm going to do 836 divided by 5 times 4.18 for water, giving me a delta T of 40 Kelvin. And I can keep 2 sig figs in that. For aluminum, I'm going to get a much larger delta T. And actually, to put that in 2 sig figs, I'm going to just change that to 170. That's a really huge difference because this low specific heat for aluminum. So what we actually find here is that we would end up with a very hot piece of aluminum compared to the final temperature of the. Oh, wait a second. Not quite agreeing with that. Sorry. That should be 303 plus 170. Yeah, I apologize. Checked my math on that one. Sorry, that should be 303 plus 170, which is not going to give us 498. It would actually give us 473 Kelvin. So sorry about that, Aaron. So much higher temperature because of that lower specific heat. This is the old regions question I was thinking about. We have a 5-gram sample of liquid ammonia, originally at a temperature of 210 K. The diagram of the partial heating curve below shows the vaporization of the sample of ammonia at standard pressure due to the addition of heat. The heat is not added at a constant rate. So what you have to attend to here is the fact that we have different physical properties. So these are different, although this is kind of close to water, it's a little bit weird, but these are different physical properties than what you see for liquid water. So here are some problems to try, and I'm going to stick the answers up to these in just a moment with work.